Let's consider an example where we multiply two numbers, and let's start with the decimal case. So considering the numbers minus 0.3456 and the numbers 0.7541, the product of these two numbers will be minus 0.26061696, and that is of course easily verified. The multiplication of two numbers in binary form can be carried out the same way. So the numbers 0.1101 in binary form and minus 0.1011 also in binary form would yield the product minus 0.10001111 in binary form. And these two examples have a thing in common, namely that if we used the digits in order to represent the original numbers, so 4 digits in this case, typically to represent the product of these numbers we need 2 digits, or 8 digits here if we discount the leading 0 and the sign. Now that is a problem in fixed point implementations, since we do a lot of multiplications and we need to handle the fact that we need more digits in order to represent the product in some way. So we consider a simple example of an AR1 circuit. So we have an input signal which gets time delayed and multiplied by a coefficient and added to itself in the feedback part of the AR1 circuit. Now if we assume that x of n is in the range minus 1/2 to 1/2 and kept in b plus 1 sign bit magnitude, and we assume that the a1 here is also in the same range, also in b plus 1 bit sign magnitude representation, then how many bits would be required in order to store the output y of n? So if we look at this problem, we see that x of n enters into the circuits, gets time delayed and multiplied by a1. And since we have b bits for the magnitude, typically we would need 2 b bits after the multiplication in order to store the magnitude of the product. We don't need additional bits to store the sign. However, that number would get added back, so we would have a 2b plus 1 bit representation here, which would get time delayed and again multiplied with a1. So now we would need 3b plus 1 bits in order to store the results, and this would never end. So in the limit we would need an infinite number of bits in order to store the output y of n in such a circuit if we wanted to do exact computations. And this is of course infeasible for a practical system. So what has to be done whenever you multiply two numbers in a fixed point implementation, or a floating point implementation for that matter, you must generally re-quantize the results back to fit within your number format once you have done the multiplications. So in the b plus 1 bit sign magnitude representation, as soon as we have carried out this multiplication, we must essentially discard the added numbers that were created in the multiplication in order to have a new number which fits within our number format. And this introduces a quantization noise that applies whenever you do a multiplication in the circuit. So looking at the base implementation of having a signal x of n, which get multiplied by a constant a here to yield an output signal. What happens in a fixed point implementation is in fact that you have the signal x of n, it gets multiplied by this coefficient, but then immediately after it gets quantized in order to fit within the number format to yield the output y of n. And we can analyze that using our additive noise model for quantization noise. So this base implementation of a simple multiplication would in this analysis be replaced by an input signal multiplied by a coefficient, but then we model the quantization in order to stay within the same number format with an additive quantization noise, which leads to the output. So in the simple AR1 filter implementation where we had this multiplication, so this is fine if we consider real-valued computations, but if we want to understand the effects of a fixed point implementation, the way to do this, or the way to model this, would be to add a noise source that is due to this multiplication. And by doing that, we may study how much of the actual signal that we want is present in y, and how much of y is due to this quantization noise introduced by quantization within the circuit. So the way to understand this would to split this signal. So because of linearity, we can consider the effect of the two different signals separately. So we would have an input signal x of n, which we could use to compute a corresponding output through a real valued assumption of this circuit. But then in order to model the fixed point implementation effects, we also have this noise source, and we can consider that independently as an input to the system, yielding a part of the output ye of n here, which is due to the noise. So we could split the corresponding output signal of the fixed point implementation into the desired part, which is due to the input to the system, and the part due to quantization noise. And we could look at the relative power of these two as a measure of how well the system is implemented using our fixed point implementation. So the power of the quantization noise that would be introduced into the system at this point would be given by the resolution of our number representation system. So in the case of signed magnitude representation, we have already achieved the result that the quantization noise into this system would be 2 to the minus 2b over 12. Now, if we wanted to know how much of that noise reaches the output, we have to take into account the fact that this noise is not just inserted to this point and added to the output, but it in fact sees the whole circuit from the point where it's implemented. So the noise that results from a multiplication would add to the output, but it would also be time delayed and fed back and multiplied with itself, which would in turn add some extra noise, and it would pass around like this. So the way to figure out the total power of the noise at the output would be to, at every single time step, you add this quantization noise at this point, and you look at the power of this noise as passed through this whole circuit. And one can show that the power of the output due to this noise is the power of the input of the noise times the impulse response of this system squared and summed up over all time. And this is equivalent to just taking the power spectral density of the noise, which we assume is a white noise process, so it's spectrally white, multiplying it with the squared magnitude of the transfer function of this filter and integrating over this range of allowed normalized frequencies. But typically for computation, the first form involving the impulse response will be the one that leads to more tractable computations or an easier mathematics. So looking at this particular example of the AR1 circuit where we have a multiplication by A. So what will the noise power be in this particular case? Will it be 2 to the minus 2b over 12 times 1 over 1 minus A? Or will it be 2 to the minus 2b over 12 times 1 over 1 plus a squared? Or will it be 2 to the minus 2b over 12 times 1 over 1 minus a? The correct answer is option number 3. It would be 2 to the minus 2b over 12 multiplied by 1 over 1 minus a. And one simple way of seeing that this is the reasonable explanation is that if you chose A to be very close to unity, you would make the whole system very close to being unstable. So in particular, if A would be outside of the range minus 1 to 1, this would be an unstable system. So you would have an infinite amplification of the input noise at this point. So that discards the second option, because if A here is larger than or approaches 1 or minus 1, this wouldn't blow up. This one would blow up if A approached 1, in which case we would get 1 over 0, but it wouldn't blow up if A approached minus 1. So this is the only one showing the correct behavior as A approaches either minus 1 or 1. And one can of course also do this explicitly by working out the impulse response of this system. So the impulse response of this system is a simple AR tapering off with this constant A here. So this would be the impulse response of an AR1 system, and once you take the squared magnitude, you get A to the 2n, which you sum up and you get this expression through an explicit computation. Now, this prescribes how to analyze a fixed point implementation of a circuit. So what we would do is we would look for every multiplication which happens within the circuit. At each such multiplication, we would add the noise source E1 to EM if you have M multiplications in the circuit. Then we would look at the contribution of each of these noise sources to the output, and there we would make the assumption that each of these noise sources are uncorrelated, and therefore we can simply add the respective power caused by any particular noise source. And what we would do in order to get the power of that noise as seen at the output would be to first of all take into account the amount of noise power at the insertion point, but then also factor in this sum of the impulse response of the system from the point of insertion to the output in order to account for the filtering of the noise before it reaches the output. Then we would obtain the total noise by simply adding up the different noise sources for the m different multiplications. This has implications for how we implement filters in fixed point. So different implementations can be better than other implementations. So if you consider the case of an AR2 filter, here shown with coefficients A1 and A2 from an input to an output, if it turns out that the poles of this system given by this equation are real valued, then you could, with real valued computations, implement the same system as the cascade of two first-order systems. And this would have implications on the resilience towards quantization noise if they were implemented in fixed point. So if we wanted to analyze these two systems, we would look at where are the multiplications. So here and here in the first system, and here in the second system. And we would add noise sources corresponding to those multiplications in order to analyze the effects of a fixed point system. So the thing is, even if the original systems were equivalent, these two systems are not equivalent simply due to the fact that the noise insertion points are different in the two systems. So if you look at E1 in this system, it would pass through the entire AR2 process or system before reaching the output, as would E2 here. In case of E1 in this particular system, it would pass through this first part and also the second part before reaching the output. So it would see the whole system of this case, which was equivalent to the AR2 system. So for this one, there is no different. However, if you look at the second noise source, it will only pass through this smaller AR1 system before reaching the output. And that will affect its power as it reaches the output. So these two different implementations will have different noise power at the output due to the fixed point effects. And it's not generally possible to say that this system is better than this system or vice versa, but it would depend on the particular constants involved. But you could of course figure this out by studying the impulse response from the input of any noise source to the output in both of the systems, adding up the squared impulse response over time and computing the corresponding effect of the quantization noise to the output signal to figure this out for a particular set of coefficients in the original system and corresponding set of poles for that equation. So to summarize, we've seen that fixed point circuits can be analyzed statistically by simply injecting noise into the circuit, and the way to do this is to insert this noise at each point of multiplication. And this is simply due to the fact that a multiplication, to be exact, requires a larger precision to store the product. And since we cannot do this in a fixed point implementation, we need to round off the signal every time that we do a multiplication or quantize after multiplication. So each noise source due to one of such multiplication in a fixed point implementation will contribute to the overall output noise of the system. And we had a formula for the contribution of each particular noise source involving the impulse response from the point where this is inserted to the output. And what this implies is that different implementations that in real valued computations would be equivalent in terms of having the same transfer function may show different performance once we implement them in fixed point, simply because the noise insertion points will be different and depend on how we implement actual circuits. So we could choose our implementation to yield good fixed point performance in terms of quantization noise.